Hello again. In this topic, we're going to look at a concept that is important to building calculus, and it's the idea of continuity. And then we're going to look at a result of that continuity, the intermediate value theorem. Now, the basic concept of continuity is fairly intuitive. The idea is a function is continuous at a point if you could draw the function at that point without picking up your pencil. It seems fairly simple, but mathematicians, they can't just go with that intuition. They have to have a mechanism by which to prove things. And so here's a more formal definition. A formal definition of continuity says that a function f is continuous at a number a at a point if the limit as x approaches a of the function is equal to the function evaluated at that a. So this gives us three things, actually, that we have to verify in order for a function to be continuous at that point a. First, the limit as x approaches a of the function must exist. We have to be able to evaluate the limit of the function at that point. Second, the function at that a value must be defined. And then finally, those two pieces, the limit must exist, and we assume it has then some value, and the value of the function at that a, at that number a, those two pieces must be exactly the same, right? So the limit with x approaching a of the function, what we learned from part 1 in a sense, must be exactly equal to what we learned from part 2. And so then, using this, we can talk about the continuity at a point, but we can also talk about continuity over intervals. And just generally speaking, we say that a function is continuous on an open interval I if it's continuous at all points in that interval. All right, so remember, an open interval might be like a comma b. An open interval says parentheses, not including the endpoints. In a later slide, we'll talk about continuity over closed intervals. All right, so here's the graph of a function, and I think we actually saw this function earlier in talking about limits. But here's a function, and based on this graph, determine where the function is discontinuous. Where is it not continuous? Explain each discontinuity, and then over what open intervals is the function continuous. All right, so again, intuition. If we were to graph this, if we were to move from left to right, where would we have to pick up our pencil? I see 4 places where I would have to pick up my pencil to draw this function. All right, so where is it discontinuous? Well, let's just assume that this is the x-axis. All right, so we have a discontinuity. And then let's explain why. Why is it discontinuous at each of those? All right, we have a discontinuity at x equals -3. So let's explain why. All right, so it looks like as x approaches -3, the limit exists. The limit is 2. However, the function value at -3 is 5. So the reason would be that the limit as x approaches -3 of f of x is not the same as f of -3. That's the reason why we have a discontinuity. Our next discontinuity appears to be at -1, when x equals -1. Why do we have that discontinuity? Think back to the previous slide, and there are 3 specific reasons why we could have a discontinuity. Which reason is it? At x equals -1, if we look at the limit from the left and from the right, we see that they are different numbers. The limit does not exist. The limit as x approaches -1 of the function does not exist. So therefore it cannot be continuous at that point. The next discontinuity is at x equals 1. And then again at x equals 2 we have a discontinuity. Explain the reasoning behind those discontinuities. At x equals 1, the limit exists. Right? As we approach 1 from the left and from the right, the limit exists and is -1. However, the function is not defined at x equals 1. F of 1 is not defined. Discontinuity. At x equals 2, we again see the limit not existing. The limit as x approaches 2 of the function does not exist. So those are the discontinuities of the function. Now, everywhere else, the function appears to be continuous. Over what open intervals is the function continuous? All right, so where is this continuous? All right, so if we assume that the function continues on to the left and to the right, then I would say that this function is continuous from -infinity to -3, then from -3 to -1, then from -1 to 1, then from 1 to 2, then from 2 to infinity. Those are the open intervals where this function is continuous. Now we're going to adjust this in a few moments because we're going to talk about, well, we can actually have continuity over closed intervals as well. So we're going to adjust this definition just a little bit in a few moments. So now let's actually talk about that. What does it mean to be continuous on a closed interval? Well, basically, if the function is defined on the closed interval, and the function is then the function is continuous on that closed interval. Notice how we have brackets here, right? Closed intervals have brackets at the endpoints. If we can show that the function is continuous on the open interval, so from a to b, but not including the endpoints, and then we can show that the left limit or the right limit, whichever is appropriate, is equal to the function at that endpoint, then we have continuity at the endpoint. So if we're thinking about a, where a is the left boundary of the interval, then we want to prove, we need to show that the limit as x approaches a from the right of the function is equal to f of a. Similarly, if we were looking at the right endpoint, b, we would want to show that the left limit, the limit approaching b from the left of f of x, is equal to f of b. And we can adjust this for half open intervals. So for example, we could talk about so when we're talking about a half open interval, we could say the interval a comma b bracket, or we could talk about the interval bracket a comma b, half open or half closed, right? It just depends on your perspective. So let's look at this previous graph in this exercise. If we, and I haven't changed the graph, but what I see here is I have a solid point at the point negative 1, 4. What this means is that the limit as x approaches negative 1 from the left of the function is equal to the function at negative 1. And I have a similar situation here when x is 2. The limit as x approaches 2 from the left of the function is equal to the function's value at 2. And so I can revise my understanding of the continuity of this function as such. The function is still continuous from negative infinity to negative 3, open. That hasn't changed. However, I can see that the function is continuous from negative 3, open at negative 3, to negative 1, closed. Since the limit as x approaches negative 1 from the left of the function is equal to the function at negative 1, I can say that the function is continuous on the interval negative 3 open to negative 1 closed. The function is then continuous, again, from negative 3 to 1, and then from 1 to 2, closed at 2. And then again, from 2 to infinity. Now you might say, well, if the function is continuous at negative 1 on the left, why isn't it... Oh, and I wrote that third interval wrong. Let's fix that. Not negative 3 to 1, negative 1 to 1. Sorry about that. If the function was continuous from negative 3 to negative 1, including the negative 1, and then from negative 1 to 1, why isn't it just continuous from negative 3 to 1? Well, obviously the function is not continuous at negative 1. We can clearly see that there's a break there. We've shown this idea already in the previous slide. We know the function is not continuous at negative 1. So we cannot just say, well, it's just continuous from negative 3 all the way to 1. It just doesn't make sense. Okay, so that's how we can define continuity on a closed interval or a half open or half closed interval, depending on how you think of that. All right, so here's a piecewise defined function. We have the function is x cubed minus x if x is less than 1, and the function is x minus 2 if x is greater than or equal to 1. And so I'd like for you to determine the continuity of the function at 0 and at 1. All right, so think about what we learned on the first slide and see if you can figure out the continuity of the function at those points. Oh, I would recommend that you pause to try those out on your own. All right, so let's see. At x equals 0. What do we need to prove? We need to prove that the limit with x approaching 0 of the function is equal to the function at 0. Well, the function at 0, that's probably the easier case. The function at 0, so I would say, well, if 0 is less than 1, so that would be 0 cubed minus 0, that's 0. Now the limit as x approaches 0 of f of x, well, if x is 0, then x is less than 1, and so I have x cubed minus x, which is a polynomial function, and so I can evaluate the limit as simply being 0 cubed minus 0, which is 0. So 0 equals 0, and so what I can say is the function is continuous at x equals 0. at x equals 1. Let's see what we have here. The limit, we would need to prove that the limit as x approaches 1 of the function is equal to f of 1. Again, f of 1 is probably easier to figure out initially. F of 1, so that's equivalent, right? X is equal to 1 here, using the second case of the function. And so that would be 1 minus 2, which is negative 1. All right, now let's see. What about the limit as x approaches 1? Well, here I have to break this up into different cases since I have a piecewise defined function. What's the limit as x approaches 1 from the left of the function? And the limit as x approaches 1 from the right of the function. If x approaches 1 from the left, remember that means that x is less than 1 here. And so then I would use the x cubed minus x rule. And so that would be equal to 1 cubed minus 1, which is 0. If we had then the limit as x approaches 1 from the right, here x is greater than 1, and so I would use the x minus 2 rule, and so that would be 1 minus 2, which is negative 1. These values are not the same, so this limit does not exist. And so therefore it cannot be equal to negative 1, so we cannot prove that the function is continuous at x equals 1. So we would say the function is discontinuous at x equals 1. So now let's talk more about some functions and see if we can find some patterns for continuity. So first, let's think about the function 1 over x squared minus 4. Where is it continuous? Well, we see that it's a rational function. All right, so here we have a rational function. And so we know that we can find limits at any values where the denominator is not equal to 0. And so, right, if we remember back to finding limits, we know that the limit as x approaches a of this function will be equal to f of a as long as, in this case, as long as the denominator is not equal to 0. So let's see, where is x squared minus 4 not equal to 0? Well, let's solve let's say, where is that equal to 0? That's maybe easier to solve. Where is x squared minus 4 equal to 0? So then that factors as an x plus 2 and an x minus 2. So then that implies x equals negative 2 and x equals positive 2. Those would force the denominator to equal 0. And so we expect discontinuities at those values. All right, so what we've said here is the limit as x approaches a of f of x will be equal to f of a as long as a is not equal to negative 2 or 2. So the function is continuous everywhere else. From negative infinity to negative 2, then from negative 2 to 2, and then from 2 to infinity. You might say, well, gosh, that sounds familiar. That sounds like the domain of that function. And it is, in fact. If we think about the function 1 over x squared minus 4, the domain of this function is the same as where it's continuous. And that's not a coincidence. Let's look at a graph of the function in Desmos real quick. So here's the graph, and we can see that there are discontinuities in the graph at -2 and at +2. And in fact, there are vertical asymptotes for that function at those values. And we should have learned about those back in an algebra course. So that shouldn't be a surprise to us that there's discontinuities at -2 and 2. But what we can now also say is that the function is continuous everywhere else. Let's look at another one. What about the function cosine x? And if you think about the graph of the cosine function, there were no breaks in the cosine function. And so the cosine function is continuous everywhere. You could draw the cosine function from, well, any beginning point to any end point without picking up your pencil. Now, of course, we can't draw the entire function because it goes on indefinitely, but it is continuous over all reals, which is, again, the same as the domain of the cosine function. All right, this one's a little bit trickier. What if we had the function f of x is the square root of x squared minus 9? Well, hey, we've seen the last couple examples, and they had something to do with the domain. Let's think about the domain and see if that makes sense to us. All right, so if we think about the domain of this function, since it's an even root, we would need the x squared minus 9 to be greater than or equal to 0. All right, so we've learned how to solve polynomial inequalities by first solving the polynomial equation. All right, we solve x squared minus 9 equals 0, and that gives us the roots x equals -3 and 3. I hope you can do that part either by factoring or using a square root property or the quadratic formula if you absolutely have to. Second, we set up our number line. And we test each interval, right? Our number line is now broken up into 3 intervals, and we test each interval. Into the x squared minus 9. So for example, if I was to test, how about -5? Then I'd have -5 squared minus 9, that's 25 minus 9, which is positive. That's greater than 0. All right, so this ends up giving us a solution. And then if I test somewhere in between, say 0, if I test 0 squared minus 9, that would be -9. That would be less than 0. That's not a solution of that inequality. And then if I test a number greater than 3, how about, just for symmetry, let's test 5. 5 squared minus 9 would, again, be positive. That's greater than 0. And so that would give us a solution, or solutions of the inequality. And so then the domain of this function, taking all this into account, what we can say is the domain of the function is -infinity to -3. Now, would we include the -3? Since it's an or equal to inequality, all right, since we have an or equal to inequality, then we can include the endpoints. So I'd have -infinity to -3 bracket, and then 3 to infinity. So that's the domain of this function. And if we think about it, it should seem reasonable that that's where this function is continuous. Because those are all the points those are all the x values that I can put into this function. And anywhere that that would cause issues would be between the negative 3 and the positive 3. All of those values, that's where the function is not defined. And in fact, let's bring up Desmos again, and let's take a look at the graph of this function, square root of x squared minus 9. And there's the graph of that function, the square root of x squared minus 9. And what we can see is it continues off to the left, stops at negative 3, and we have a solid point at negative 3, 0. And then it picks back up at 3, 0, and continues to the right. It's continuous over its domain. Oh, that should be a bracket. And so, I hope you can see over these previous 3 examples that we have a pattern forming here. For all of our traditional functions, there was a connection between the domain of the function and the continuity of the function. And that's not a surprise to me. In fact, the following functions are continuous on their domain: a polynomial, rational, radical, trigonometric, exponential, and logarithmic functions. All of the functions that we've learned through all these standard functions that we've learned through our algebra courses are continuous on their domains. Now, what's also important is that if we have functions that are continuous, then algebraic combinations of those functions are also continuous on the intervals. So if we add or subtract functions, the continuity stays the same. If we multiply a function by a constant or by another function, the continuity doesn't change. If we divide a function by another function, the continuity is the same, except for where the denominator could equal 0. That shouldn't come as a surprise. And then nth powers and nth roots. Now for nth roots, for this one we have to be a little more careful, right? For the nth root, if n is even, then f must be greater than or equal to 0. Right, your function must be positive, or non-negative is the better term. The function must be non-negative for continuity. But generally speaking, if you can figure out the domain of a function, of an algebraic function, then it will be continuous on its domain. So here we have the function x squared minus 2x minus 8 over x minus 4. And I'm stating first that this function has a discontinuity at x equals 4. Why is that true? We know that there's a discontinuity at x equals 4 because the domain of this function is the set of x such that x cannot equal 4, which is equivalent to, right? So this is exactly equivalent to negative infinity to 4 union 4 to infinity. All right, because if we let x equal 4, it would give us a 0 in the denominator. And we've seen that that's an undefined expression, and so then we must have a discontinuity there. Now the second part, how could we redefine this function to remove the discontinuity? So the second part's a little trickier. So if we wanted to remove the discontinuity, we would have to force the function to be continuous, right? To remove a discontinuity, we would have to force the function to be continuous. You might say, well, isn't there a vertical asymptote here in this function? And there isn't. Let's take a look at this function. Let's graph it. All right, so let me graph this in Desmos. All right, so I have the function x squared minus, it was minus 2x minus 8 over x minus 4. You might say, well, gosh, that looks just like a line. There's no vertical asymptote at x equals 4. Why is this happening? Well, it looks like everything's okay at 4, but really, it's not. This graph is slightly incorrect because we know that at x equals 4, this function is undefined. So we've got to be very careful about how programs graph functions. And if you graph this on a graphing calculator, you're probably going to get a similar graph. But really, the graph of this function is a little different. There is what's called a removable discontinuity in this function. If I was to graph this function, here's how I would represent it. So there's the same rough graph. And there should be an open point here at x equals 4. Now let's understand why. We see, if we were to take the limit as x approaches 4 of the function, that's the limit with x approaching 4 of x squared minus 2x minus 8 over x minus 4. And we know that we cannot directly substitute because the 0 is a denominator. But in fact, if we substituted 4 in the numerator, 4 squared is 16, 2 times 4 is 8, another 8. We have 16 minus 8 minus 8, we get a 0 in the numerator as well. This is an indeterminate form. So if we apply a little algebra, this is a limit with x approaching 4 of x minus 4 by x plus 2 over x minus 4. And so then this is the limit with x approaching 4 of x plus 2, which is 6. And so we have an open point on this curve at 4, 6. Now, I called it a removable discontinuity because I can redefine the function to make it continuous. And here's how I would redefine it. Call g of x the piecewise defined function f of x if x is not 4, and call the function 6 if x equals 4. Now, this is a continuous function because I know that the limit as x approaches 4 of g of x would be then the limit as x approaches 4 of f of x, because if we're approaching 4, we're not equal to 4, we're just getting close to 4. So the limit as x approaches 4 of g of x would be the limit as x approaches 4 of f of x, which would be 6, and g of 4 is also equal to 6 by definition. So here's how we could redefine the function to make it continuous. One important result of continuity is what's called the intermediate value theorem. And basically it states that if we have a continuous function and there's some value between the function values. We have a function that's continuous on a closed interval AB. And if f of a is less than f of b, and m is some number between them, and really we could say or f of a is greater than m, which is greater than f of b, it's a similar statement, then there must be some c on the open interval AB such that the function evaluated at that c is equal to m. This is called an existence theorem. It tells us that the c exists. It doesn't tell us how to find the c, only that it exists. And in fact, it doesn't tell us that there's only one c. It only tells us that there is at least one. And here, this graph that I took from the Paul's online notes page, we can have many c values that meet the condition. Now, I'm not going to prove this theorem because the proof of this theorem is well beyond the scope of this course. It's a fairly difficult theorem. If you're interested in it, you can look it up. This is a theorem that would be proven in an advanced calculus course. So you math majors, you might get to see this maybe in your senior year, the proof of this theorem, if you don't look at it right now. All right, so an immediate result of this intermediate value theorem is it allows us to find that roots of an equation must exist. It doesn't, again, tell us how to find them, just that they must exist. So let's see an example of how we could use the intermediate value theorem to prove existence of a root of an equation or a function. So here we're asked to show that there is some x on the open interval 0, 1 such that the cube root of x is equal to 1 minus x. So I'm going to change this up a little bit. I'm not going to start here, but what I'm going to say is that this is equivalent to saying that the cube root of x plus x minus 1 is equal to 0. So here's what I'm going to show. First, I'm going to let f of x be equal to the cube root of x plus x minus 1. Now, I know that the cube root of x has domain all reals. I know that x has domain all reals. And negative 1, a constant, of course, has domain all reals. So, I know that the function is continuous on negative infinity to infinity, and since it's continuous on negative infinity to infinity, so it must be continuous on the recommended interval 0 to 1. Since f of 0, what's f of 0? F of 0 would be 0 plus 0 minus 1. F of 0 is negative 1. And f of 1 would be 1 plus 1 minus 1 is 1. And 0, that's the value we're looking for, right? And f of 0 is less than 0, which is less than f of 1. Then, by the intermediate value theorem, there must be some c on the interval 0 to 1, left endpoint, right endpoint, such that f of c equals 0. Because the function is continuous, and our goal value 0 is between the function at the left endpoint and the function at the right endpoint. There must be a c value. There must be some value in between such that f of c equals 0. And again, this doesn't tell us how to find it. It just tells us it exists. But sometimes that's enough, just that something exists. Alright, so that concludes this topic on continuity and the intermediate value theorem. Thanks for watching the whole thing. See you next time.